Ready to go?
Yep. Yeah.
How's the live streaming thing? Good? Okay.
Good.
Okay. Okay, hello everyone, welcome back for the last talk of today. We're happy to have Kaan on there telling us about chiral gauge dynamics, candidates for non-supersymmetric dualities. You know it?
Thank you very much. Thanks for the lovely events so far as well. Yeah, I'm going to be talking about some of our work. Well, myself, I'm the transit, I'm my supervisor David Tong, who's obviously in the audience. And that's the slide light, it's just going to be a single candidate for non-SUSY dualities, so sorry about that. So I'll just start with a sort of gentle introduction. Of course, as you all know, without supersymmetry, our understanding of some of the most basic questions about strongly coupled 4D gauge theories remain lacking. And for example, we know when we have supersymmetry, we can have interesting dynamical behaviors such as confinement without symmetry breaking. It could be where two theories flow to the same fixed point. It might be a SUSY theory flows to another gauge theory with emergent gauge bosons. And this is all under control, but I think it's safe to say without supersymmetry, it's not well established if any of these phenomena can persist. And of course, there's proposals in the literature, and we'll try to add to some of those today, but it's just hard to keep track of the dynamics. And more concretely in this talk, I'm going to be talking about some non-supersymmetric SUN chiral gauge theories, and we're going to ask if they might behave like some of the supersymmetric theories I've mentioned before. And again, just to stress, in this task, we're going to sort of, I guess, fundamentally fail. It's not going to be very concrete, but I'm going to try and give you some sort of consistent proposals for these dynamics. And for this, we have a few tools at hand. The main ones, as always, going to be symmetries and anomalies. Then we're going to use the A theorem, which sort of formalizes the idea that degrees of freedom must decrease under RG. And then we can also look at the large N limit. I'm not actually going to be talking about this in this talk, but if anyone's interested in it, please come and ask me afterwards. And here, I just wanted to sort of point that if we had vector-like theories, like QCD, we could, of course, also do lattice simulations to get some intuition. In these chiral theories, this is impossible. And sort of on a related vein, for vector-like theories, there's general theorems such as the Waffler-Witten theorem and the Weingarten theorem, which can again constrain the possible dynamics in a very powerful way. These also don't work for these chiral theorems. And this is because these theorems all rely on the fact that vector-like theories have a positive definite or positive semi-definite path into the measure, and without that, they just don't work. So I think that's also morally why you might expect some chiral theories to behave like supersymmetric theories, because also if we add scalars, then again the measure loses this property, and these theorems again don't work. So in that sense, chiral and supersymmetric theories might be similar in the sense that these theorems don't work, and we might expect some similar dynamics. But anyway, obviously three tools aren't that much, but it's all we have, so we're going to try to use them to give some proposals. So the first theory I'd like you to consider is an SUN gauge theory with a collection of left-handed Weyl fermions. The fermions transform in this way, so SUN is the gauge group, so there's an adjoint fermion, there's a symmetric, and then there's a bunch of fundamental and anti-fundamental fermions. You need to take the number of flavors Q to be n plus p plus 4 to cancel any gauge anomalies. And the rest is just the continuous part of the global symmetry group is what's written here. I'll comment about the discrete symmetries later on. And this theory has 21 Toft anomalies. The values obviously don't matter, but just want to emphasize there's a lot of them. And so yeah, okay, that's the first theory I'd like you to keep in mind. The second one is a very different gauge theory. This is roughly a spinate gauge theory. Yes, yeah. Sorry, it is, yeah.
On the right, S squared,
What's that, sorry?
the one anomaly S squared.
Oh yeah, sorry. So that's meaning there's a mixed anomaly between SU, say Q squared, and the U1. Yeah, sorry, actually. So the second theory is roughly a spinate gauge theory. I'll talk about what that roughly means in a second. And again, it has an adjoint fermion. It has charged fermions in the vector, spinor, and conjugate representation, and also for singlet fermions as well. And so the whole point, I guess, of this talk is that the global symmetry structure, at least the continuous part so far, matches that of the chiral theory I just introduced a bit earlier, and also all 21 Toft anomalies match in sort of quite a non-trivial way. And just to comment here, of course, these singlets, they have to be endowed with these specific global quantum numbers, and you can do that by adding some scalars and writing some marginal Mikawa terms, or you can do that by these 4 fermion irrelevant terms.
So, could you go back one slide? Just sure. Where does the n enter into the spin 8 gauge theory? Is it some?
Yes.
What does the n mean in this case? It's
I
not the
see.
rank of
Yes.
the gauge
Yeah.
group.
So the n sits well in the U1 charges, but also in the Q as well. The Q is the same Q.
Q is correlated with n by some formula.
Yes,
I see.
by
Okay.
this one here.
Okay.
Anomaly.
Thank you.
But also, you might ask why spin 8? Why is the 8 there? And that's sort of numerology, where in 4D the anomaly coefficient for SUN is, for the symmetric and anti-symmetric fermions, is n plus 4 or n minus 4, and it's just that difference is why you need the 8 to cancel anomalies to get the whole thing to fly.
So U1, 1, 2, and are all good on the quantum corrections. So
Yeah.
they don't get blocked. So
Yeah, the normal numbers. Yeah. Sorry?
That should probably be bounded by like a beforehand. It's not a double.
No, yeah. Okay, and so that's the sort of starting point, the anomalies match, and in the rest of the talk we're going to be asking, well, does that mean anything? Why do we care? Might they be related dynamically? And to that end, obviously the first step could be to try and supersymmetrize both of these theories. They both have adjoints, so it makes sense to just add some scalar partners to the other fermions, and then we have some control, we can make some progress. And in fact, when P is 0, this has been done. You can do this on both sides, and this is the famous Pugliese-Strasser duality. And the P greater than 0 case is a sort of extension of this. But here we run into a problem. Or I should say, there's no issues with the chiral theory. You can just add some scalar partners to the fermions, and it all works out. But it turns out there's a problem with the spin 8 case, and initially that's sort of we can make some progress. And in fact, when P is 0, this has been done. You can do this on both sides, and this is the Strasser duality sort of comes from. And the P greater than 0 case is a sort of extension of this. But here we run into a problem. Because of the anti-symmetric. Or I should say, there's no issues with the chiral theory. Try to write out potentials. Everything we have is fermions, and it all works out. So it's just hard to. But it turns out there's a problem with the spin 8 case, and initially that's sort of we can make some progress. And in fact, when P is 0, this has been done. You can do this on both sides, and this is the Strasser duality sort of comes from. And the P greater than 0 case is a sort of extension of this. But here we run into a problem. Or I should say, there's no issues with the chiral theory. And actually, the potential is everything we have is fermions, and it all works out. So it's just hard. But it turns out there's a problem with spin 8 case, and initially that's sort of we can make some progress. And in fact, when P is 0, this has been done. You can do this on both sides, and this is the Strasser duality comes from. And the P greater than 0 case is a sort of extension of this. But here we run into a problem. Or I should say, there's no issues with the chiral theory. And actually, the potential is everything we have is fermions, and it all works out. So it's just hard. But it turns out there's a problem with spin 8 case. And initially that's sort of we can make some progress. And in fact, when P is 0, this has been done. You can do this on both sides, and the Strasser duality comes from. And the P greater than 0 case is a sort of extension of this. But here we run into a problem. Or I should say, there's no issues with the chiral theory. And actually, the potential is everything we have is fermions, and it all works out. So it's just hard. But it turns out there's a problem with spin 8 case. And initially that's sort of we can make some progress. And in fact, when P is 0, this has been done. You can do this on And straight away, something that might make you nervous is if you look at this.
Well, I should say, there's no issues with Chiral. But it was not the problem with
that's
initially that's and in fact, the key is
and straight away, something that might make you nervous is if you look at this.
well, I should say, there's no issues with Chiral. But it was not the problem with initially that's and in fact, the key is
and straight away, something that might make you nervous is if you look at this.
well, I should say, there's no issues with Chiral. But it was not the problem with initially that's
and straight away, something that might make you nervous is if you look at this.
well, I should say, there's no issues with
and straight away, something that might make you nervous is if you look at this.
well, I should say, there's no issues with
and straight away, something that might make you nervous is if you look at this.
well, I should say, there's no issues with
and straight away, something that might make you nervous is if you okay, so that's what we say. And now it's like and when you okay, so that's what we say. And now it's like okay, so that's what we say. And now it's like and now it's like Too far off. Too far off. Following up on that, one comment following up on that, one comment following up on that, one comment following up on that, one comment
Yeah.